We have wrapped up our exponential and log unit, and we're going to put it together with exponential and log application problems. So I'm going to run through some of these problems just to make sure that you're able to set them up as you go through solving. So to start, we've got the formulas up on top for our exponential growth and decay. This formula is the one that you're going to use when you have compound interest and they give you a specific amount of time. So monthly, quarterly, semi-annually, and so on. That would be your n values. When it says compounding continuously, that's where we're using that PERT equation. For simple growth and decay, we're using the 1 plus or minus r. So if it is appreciating, so increasing, you're going to use the plus. If it is depreciating or decreasing, then that's when you would use the minus here. And then our basic growth and decay is this one right here. So we're going to use this one for the doubles, triples, half-life, and those that give us the growth or decay factor. All right, so we'll start with the first one here. It says mathematics invest $10,000 at 8% annual interest and leaves it there for 10 years. What is the total amount in his account at the end of 10 years? This is actually the easiest type of problem we get. In this case, they're asking what our total amount is. So they're asking for this A at the end of our equation. And so all we have to do is plug it into the calculator. But we want to make sure we use the correct equation. It is not compounding. So we're looking at the regular growth and decay right here. So we get A is equal to P is our initial amount of 10,000. It is growing, so we are going to do 1 plus. When we put a percentage in here, we move the decimal over 2 places, so this would be 0.08 to the t power. Sorry, and we know the t is 10. And so we'll plug in 10 there. This is the easiest type of problem because everything is on one side and then the variables on the other side are unknown. So all we have to do here is plug this into the calculator. So 10,000 times 1 plus 0.08 raised to the 10th power. I put that in exactly, oh, you can't see that with the glitter. There we go. I put that in exactly the way it looks on my paper, so there's no order of operation issues. So we have 21,589. Since this is money, we do keep 2 decimal places for money, so this would be and 25 cents. All right. For our second one here, it says read a chapter, invest a sum of money at 6% annual interest compounded monthly. After 10 years, she has $18,193.97. How much did Rita initially invest? So what we're looking for is how much she initially invested. That's that p-value. So this problem is going to be a little bit harder because our variable is going to be on the side of the equation that has everything else. Our final amount of money was $18,193.97. So that's going to be on the left-hand side there for the A. We do not know the initial amount, so that's going to be our X or our P, whichever variable you want to leave in that place. This was compounded monthly, so I know I'm going to use this first equation here. Anytime it says compound and gives you the specific amount of time, it's this equation. So we get 1 plus, our rate is 0.06. We move that decimal over 2 places. Monthly happens 12 times a year, so our N is 12. And we left it in there for 10 years, so that is going to be our time. Now we're solving for this right here, so we're going to want to simplify this. I'm going to put that in the calculator. Keep in mind that when you put this in the calculator, it is going to give you some kind of decimal, and you want to continue to use that on the calculator, not round it. So I'm going to put in there 0.06 over 12 raised to the 12 times 10 power. So it gives me a long decimal. I can go ahead and round that to write it on my paper, but that's the one that I want to keep using when I'm using my equation. So I have that right there. Now these two are being multiplied, so I divide by 1.82. And so this is where I'm talking about using that whole long number. So I want to do the 18,193.97 divided by, and I want to use that entire thing. So I use the arrow key to highlight it and then hit enter so that it copies the entire thing. I don't round until the very end. I hit enter, and there it is at $10,000. So that was their initial investment. All right, for our next one, Stuart Dent invests $1,000 in account earning 7.3% annually. How many years will it take for Stu's money to double? So if we want to know how long it's going to take for it to double, well, double 1,000 is 2,000. So our ending amount should be 2,000. Our starting amount was 1,000. So that goes there. This is not compounded, so we're going to use the regular equation for growth. So that's 1 plus 0.073. I moved that decimal over 2 places to put it in. And we want to know how many years, so that's where our variable is. I start by dividing by 1,000. Since these two are being multiplied, and I want to get this by itself because that's where the variable is. And so we get 2 is equal to 1.073 raised to the t power. Now we've got an exponential that we need to solve for the exponent. So we need to convert this to a log. I drop my base and then switch. So 2 becomes my argument and the t is freed. At this point, we can put it in the calculator. We hit alpha window to get to our log base. In the base, I'm going to put in that 1.073. which was my base. In the argument, I put in the 2, and that would be 9.8 years. All right. Anita Loan invested $100,000 at 8.3% annual interest compounded quarterly. For how many years will she have $150,000 in her account? So my final value is $150,000. We started with $100,000, so that's my P. This is an interest compounded quarterly, so I'm going to use the 1 plus 0.083 over 4 because that's what quarterly is. That happens 4 times a year. And then 4 times t. And again, we're solving for this t. So we're going to use the same process we did up here. We would divide by 100,000. And so that gives us 1.5 is equal to, and we're going to want to simplify that there. Again, we can round when we put it on our paper, but we're going to want to continue to use that as is. So I'm going to do 1 plus 0.083 over 4. Whoops. And so that is 1.02075. Raised to the 4t power. Now our term with the variable is by itself here. It's isolated. So we are ready to convert this to a log in order to solve. I've run out of space, so I'm going to move over here. And I get a log with a base of 1.02075. My argument becomes that 1.5 is equal to 4 times t. When I put this in the calculator, I'm going to hit alpha window, go to my log base, and again, I'm going to use my arrow key to highlight that and hit enter so that it puts that entire thing in my base. And then the 1.5 is the argument. That gives me 19.74 is equal to 4 times t. My last step would be to divide by 4. And so t is 4.9 years. All right, on this next one, it says algebra buys a car for $19,500. The average annual depreciation on this model is 13%. What will the car be worth in 4 years when Al finally pays off his loan? So in this case, when we set this up, it's depreciation. So we're going to want to do minus. And we want to know our final amount, so we don't know that. So we get 19,500. 1 minus 0.13 to the t power. And in this case, that t is 4. Told us 4 years right here, so I'm going to put in a 4 for the t. This is that easier type. All I have to do is plug this into the calculator, and it'll give me my amount, which is 11,171.50. All right. We're going to go to number 8 now, and it says a population of 150 deer in a state park quadruples every 10 years. Find the population of deer in 55 years. All right, so it says quadruples. So in this case, it's giving me that growth factor. So we start with the 150. It is quadrupling, which means we're multiplying it times 4. Now, we wouldn't put t up here because then it would do it every year. It says it quadruples every 10 years. So this would be t over 10. There's my equation. Now it does give me 55 years, so I would plug in the 55 for the t. So I get a equals 150 times 4 to the 55 over 10. This is one of the easier ones because our variable's on the other side of the equation, so all we have to do is plug that into our calculator. And so we get 307,200 deer. All right, for number 9, it says Gwen invested a sum of money in an account that paid 4.6% annual interest compounded continuously. After 25 years, she had 25,265.54. How much was her initial investment? So this is probably the hardest type of problem we're going to get. It tells us our last amount is 25,265.54. We do not know the initial amount, so I'm going to leave that as P. It says compounded continuously, so that's E. Our percentage is 4.6, so that switches to 0.046. And we left it there for 25 years, so we would plug that in for the T. We want to get this by itself, and these two are being multiplied. So I would divide by E to the 0.046 times 25. We do not have to convert this to a log since what we're looking for is this part right here. So we get E to the 0.046 times 25. And now you can put that in your calculator and we find that our principal was $8,000. All right, for number 10, it says Megan bought a car for $42,000 5 years ago. Now it is estimated to be worth $20,700. Determine the average rate of depreciation for the car to the nearest 1/10 of a percent. So here our variable is going to be the rate. That's what we don't know. So the car is now worth $20,700. It started at $42,000. 1 minus, that's what we don't know, is the rate. And she bought it 5 years ago. So that's our time there. These two are being multiplied, so I divide by 42,000. And so that gives us 0.49 is equal to 1 minus r to the 5th power. In this case, our variable is inside of this 5th power here. So to get rid of the 5th power, we take the 5th root. And whatever we do to one side, we do to the other. So the 5th root and the 5 are going to cancel. Now I do want to show you how to put this in the calculator. All right, so we want to take the 5th root of this right here. So we're going to go to math. And then the cube root is number 4. But if you go to number 5 there, it's got an x in the place of the root. So that's what we're looking for so that we can put any number we want here. And we want the 5th root there. So I'm going to put a 5. And then I'm going to go ahead and highlight this so that it does take the entire amount instead of that rounded amount. We hit enter. And there it is at 0.868. So I'll just put 0.87 here. Is equal to 1 minus r. I subtract the 1. And again, I'm going to do it from my value that is in the calculator, that entire thing. So I do minus 1. And so that gives us a negative 0.132 is equal to our negative r. We would multiply both sides times a negative to get a positive 0.132. And this is a rate, it's a percentage, so we do have to move our decimal over 2 places. So our rate would be equal to 13.2%. All right. Number 12 here says a certain radioactive isotope decays from 70 to 36 grams in 15 years. What is the half-life of the isotope? So our final amount was 36. Our initial amount was 70. We're looking for the half-life. And if you remember the half-life, it is T over whatever the half-life is here. So our time is 15 years, but we don't know what that half-life is. So that's where my variable is going to be in that exponent. So now I'm ready to solve. So I divide by 70. And we get 0.514 is equal to 1/2 to the 15 over h. At this point, to free it out of the exponent, we need to go ahead and convert that to a log. I've run out of space here, so I'm going to write it over here. I get log with a base of 1/2, since that's the base on the exponential. This becomes my argument, is equal to 15 over h. I put that in my calculator, I get 0.959 is equal to 15 over h. Now we've got a proportion set up so we can cross multiply. So we get 0.959h is equal to 15. My last step is to divide by 0.959. And so we get the half-life of this is 15.64 years. That's how long it takes to get half of its initial amount. All right, our last one here is an earthquake problem. It says in 2007, several earthquakes struck Indonesia. One of them registered 7.9 on the Richter scale. One of the other earthquakes recorded that year was registered to be 4 times more intense. What was the magnitude of the stronger earthquake? Use the equation m equals log of I over 10 to the negative 4, where m represents magnitude and I represents intensity. So in this problem, we really have to put a little more thought to it. It tells us that the initial one is 7.9 on the Richter scale, so I would plug in a 7.9 there for our magnitude and get log of I over 10 to the negative 4. Now we're ready to solve for the intensity in this problem so that we can do the 4 times intensity in the other problem. I convert this to an exponential to free this argument, and so I get 10 to the 7.9 is equal to I over 10 to the negative 4. This is the common log, so it's got a base of 10 there. So when I drop the base, that's where I get that 10 from. And then they switch, so that's 10 to the 7.9 is equal to I to the 10 to the negative 4. Now we can cross multiply to solve this. And when we multiply 10 to the 7.9 times 10 to the negative 4th, they have the same base, so I'm going to keep that base and I am going to add the exponents. So I get 10 to the 3.9. You could also put that in the calculator and get a decimal approximation, but it's almost easier to work with that value. So now we're going to find what the magnitude is of the other earthquake. So we've got the magnitude is equal to log. Its intensity was 4 times this one. So that would be 4 times 10 to the 3.9 over 10 to the negative 4. Now, all of this is on one side of the equation, my variable's on the other, so we can just put that in the calculator exactly the way we see it. So we get log, the common log, so all I have to do is hit the log button. And then I'm going to go ahead and put it as numerator over denominator, and we get 4 times 10 raised to the 3.9. And then on the bottom, 10 raised to the -4. Close my parentheses, and we get 8.5. So the magnitude on the other earthquake was 8.5 on that Richter scale. That was one of the harder ones too, just because you had to put some more thought to it. There's a lot of different equations that we use in these, and setting them up is really important. So you want to practice and make sure that you can set them all up in order to then solve.